Now let's take a look at robotic locomotion. So locomotion just refers to movement. Okay, so it's a robot that is moving. So the technical definition of it is movement or ability to move from one place to another. So we just kind of use locomotion as the catch-all term, which talks about the motors and actuators that are on a robot that allow it to actually spin wheels and move its legs and move its arms. We also extend that to the arms and any sort of mechanical device that moves within the robot. But basically what we're talking about is trying to understand the DC motors on the robot and just kind of learning some of the terminology and just the theory of operation. So what I want to talk about is the science behind an electric motor, and I highlight that it's the science behind the electric motor, and then later we'll talk about the engineering behind an electric motor. And the reason we do this is it's not to become an expert in electromagnetism or to become an expert in motors, but when you deal with robotics, it's good to just know the terminology that's used and where the terminology comes from. And it's also really interesting to know kind of the core operating theory behind an electric motor. And it turns out that it can be simplified to something where you say, okay, I understand that this wire will move in the presence of a magnetic field. And if you look at kind of the beginning of an electric motor and how it was devised and the observations that were made to provide us the capability to create an electric motor, then you start kind of understanding some of the terminology. So by the end of this, hopefully you'll just have a feel for how an electric motor works and where the terminology comes from, and you'll just feel comfortable, when people are talking about electric motors, what they are. So, and then I highlight the science and the engineering, like I said, because a lot of times people don't understand what an engineer is. So most people understand what a scientist is, but then there's an emphasis on trying to develop engineering and trying to get students to go into engineering, but it's really hard to convince a student to go into engineering when they don't know what engineering is. So if we just start kind of talking about the difference between science and engineering early, then people will be able to make a more informed choice about the career that they go into, or the degree that they go into. So in general, science is a field that makes observations about the world around us, and they try to come up with models that explain what's happening. An engineer then takes those observations and those models and creates devices that benefit humanity. So in an electric motor, you'll see that the science is understanding how things, or why things are in an electric motor, why the magnetism operates the way it is, and then an engineer takes that and actually creates a device, which is the actual motor. Okay, so let's just start with the theory behind this, the science. When an electric charge moves through a magnetic field, the field exerts a force on the charge. So what does that mean? Well, let's take a look here. So let's just say we had a permanent magnet, and you have a north pole and a south pole, and there's a magnetic field between them. So we give that the letter B. So we say it's a B field. So you have this magnetic field here, and there's magnetic field lines, and it's pretty understood what a magnet is, or at least how it operates. But then what was observed is that if you moved charge through the magnetic field, okay, and moving charge per time is current, is defined as electrical current, and it's given the letter I, and it has units of amperes or amps, and you're basically the change in charge per time. So what was observed is that if you moved current through a magnetic field, a force would be exerted on the charge. So there was actually a force on those charged particles, and the force would actually pull those charges in a particular direction. And so we have a force here. Now, the direction of the force was observed was observed to be in a particular direction with respect to the direction of the magnetic field that flows from the North Pole to the South Pole, and also with respect to the current. And there's this thing called Fleming's left-hand rule that describes which way the force will be. So if you use your left hand and you put your index finger and your pointing finger out, or your first two fingers out and your thumb up, you can say that the B field, which is the magnetic field, you point with your first finger. In this situation, it would be going from north to south, and then you have your second finger. Your current is in the direction of the current, and you'll see that the thumb points in the direction of the force. Okay, so you can kind of quickly figure out which way the force is going to move in these things. So when we move charge, the way that we do that is we move it through a wire. So it's actually a physical thing, okay? So even though that the charge, if you had a particle that was flying through air, it would also have a force exhibited on it or exerted on it, and it would move. But in a practical sense, we always carry current in a wire. So if you put a wire in this magnetic field and you ran current through it, it would move. It would actually move in this direction. So this is the science. This was the observation that everybody made in the 1700s and 1800s of just trying to figure out what is going on here, and they came up with all this theory and all the math that supported how much force and how the current relates to the magnetic field strength, and how that in turn creates this, or not creates, but just explains how much force is going to be there. Okay, so now here's the engineering. So the engineers come along and go, wow, that is great. We can put current through a wire and the wire moves. Now you have movement. I can create movement by running current through something. I can create a new device. So consider this. What if you put a loop of wire in the magnetic field? Okay, so in this situation, what we're going to do is we're going to have this loop of a wire, and we're going to put a battery on it, or a voltage source. So the simplest form is a battery. So we're going to put some DC voltage on this. And this will cause current to flow in the wire. And current flows, the analogy is kind of like thinking about it as water, right? So it's going to flow in a direction, and it flows around this loop and then goes back into the battery, and it flows in this manner. Well, based on the Fleming's left-hand rule, what you'll see is if I do this loop, you'll have one side of the wire that has a force going upward, and the other side of the wire will have a force going downward, and you can actually have a rotation here. So now we're starting to get to the point where it's like I can make something spin within this magnetic field. So I'm getting close to inventing something. So this is a much better image of a DC motor, a very simple DC motor. And this is from a company called learnengineering.org. They have some just really great visualizations of some of the engineering concepts, and I went and got these from their website on a DC motor. But if you look at this, what we have is let's say a permanent magnet here, north and south. You can see the magnetic field lines going from north to south right there. And what we do here is they're going to use a bunch of wires here, okay? And you can see that the current is kind of flowing here, and you see the battery here, and you say, okay, well, what happens once I let it spin? Well, it works great. It will actually spin, except that when it gets to the top, at this point, it's not going to spin anymore. So it was able to spin, and now once it got up here, it didn't have any more force on it. And even if you allowed it to spin a little bit more, the force would pull it back up. So if you ever built an electric motor like this, or we call it a DC motor for direct current, which is what comes out of a battery. So if you built this, you would get a spin, and it would spin up, and it would just sit there. So we need some way to keep the thing spinning, and that is accomplished with what we call these commutator rings and brushes. So if you look at what a commutator ring is, we need a way, or what we want to do is once it gets up here, we actually want to switch the flow of the current. Because if we can switch the flow of the current, then this force right here, it will then flip and go the other way and go down, and then the force down here on the bottom side of the coil of wires, or the wire, will flip up. And if it has enough momentum, which it will, it'll rotate up here, and then you flip the direction of the current, and then the momentum will carry it into this region of the magnetic field. The force flips to going down, and then it'll spin down here. So if we can continually switch back and forth the direction of the current in this wire when it gets in this position versus this position, then we can get this thing spinning. So you would do that with a commutator ring. And a commutator ring it's a way to use the battery and not move the battery. Okay, so the battery is going to stay constant, and we're going to make electrical contact with this side of the wire using this portion of the commutator ring. So you can imagine that the commutator ring is going to spin. And notice that this is connected over here to the right side, and then this portion of the wire, this side of the coil of wires, is connected to this portion of the ring, and it's connected over here to this terminal of the battery. Now notice that there's a slit in here. So you actually have a slit, and what we're going to do is as this rotates around, it will change whether this light green or aqua side gets the positive side of the battery, or if the dark blue gets the positive side of the battery. So now in order to allow this ring to spin, the ring is actually connected to this coil of wires. They use these brushes right here that have springs in them, and this provides basically a mechanical connection. It's a spring that pushes these brushes down here, and it allows this thing to spin and make electrical contact. So that's how the DC motor was born. So this is the picture of the most simplest DC motor, and you can build these. There's little kits that you can build and go into elementary schools, and you can show students how these things work. You just grab a permanent magnet, you grab some wires, and you build these little brushes, and you put a battery on it, and it'll spin. And it's a great invention. Okay, so let's get a little bit of terminology, and then we'll look at a visualization or a graphic depiction of this. So first of all, the term armature refers to the coil of wires, and in this situation it's just one coil of wire, but you'll see that you can have multiple coils of wire if you want to have a more complex motor. But the armature is the term that talks about the coil of wire. The commutator ring is attached to the wire, and the armature and the commutator rings, those are the spinning things, and the commutator is used to switch the direction of the current. And then the rotor is a generic term that talks about the assembly within the motor itself that spins. So it is the spinning part of the motor. And then the brushes they have springs that push them to make electrical contact with the commutator, but they don't move, so they're going to sit in the same spot, so they're actually fixed. And then that gives us to our last term, which is the stator, and that's the part of the motor that doesn't move. So in this situation, for this simple one, the stator would consist of the battery, the brushes, and also the permanent magnet here. Okay, so those are the terms that we have. Now let's take a look at a really good visualization of how a DC motor operates. And so you see right here that picture that we had before, and you can see the B field right here. And what's going to happen is that the commutator ring right here is connected to, or the right side of the armature, the coil right there is connected to the negative. This side is connected to the positive. And so let's watch what happens as this visualization allows this thing to spin. You'll see the current is flowing clockwise around the coil of wires. That creates those two opposite forces on each side, and it causes the thing to spin. So now you're at the perpendicular portion of it. Notice what happens due to the slits in the commutator. The direction of current was switched, so then the force is switched. So as the thing goes around, you notice that by design and due to these slits, you can use the commutator rings to actually switch the direction of current, and you're doing that to switch the direction of force. So notice that the armature comes up here, and the momentum carries it down into this region, and they're just continually switching back and forth. They're switching back and forth, back and forth, back and forth. Okay, so we keep going with this visualization. So it's cranking along here, and we'll watch it for a little bit just to get a feel for it. And you can kind of see how the momentum, it slows down at the top. And this becomes a problem because if you're making a motor, you really don't want it to be not going the same speed all the time. So one of the ways you can get around that is go ahead and put another coil of wires in the rotor or on the armature, and that does require that you have now additional commutator rings. But the way that this will work is that you're actually going to have you're either going to have one coil of wires or the other coil of wires energized or current flowing through it. But what you can do is you can add more and more of these until you get a very consistent rotation around the rotator of the rotor. Okay, so then this gets more to what a current rotor looks like. Notice that they use a lot of different coils of wires. So the armature consists of a lot of different coils of wires. Each one is connected to a commutator ring right here, and you still have the brushes in there. Then one of the things that they do is they put they call it a ferromagnetic material in between them. So this would be like an iron core, and what that does is it concentrates the magnetic field so that you have essentially more force, so it makes it much more efficient. Okay, so that's how a DC motor works. Okay, so then let's take a look at another invention that allowed the DC motor to kind of evolve, and that is in the form of what's called an electromagnet. So this is another great outreach activity for elementary school students or middle schoolers, and this is an observation, so this is the science, that if you put a coil of wires, if you make a coil of wires and you run current through it, that coil of wires will actually create a magnetic field. So this is the practical implementation here. This would be one that shows the magnetic field lines. So you actually create a north and south pole. Notice that the wires are usually wrapped around some material like iron, and that again concentrates the magnetic field energy, and it allows the strength of this to be much larger. So this is fantastic because think about this. You don't need to necessarily use permanent magnets anymore. You can create your own magnets. So then that becomes the engineering behind this. So instead of making these permanent magnets, and it turns out that the permanent magnets, you know, they oftentimes use these rare earth elements, and they're hard to find, I guess would be one way, and it turns out you can make a stronger magnetic field using electromagnets. So what they'll do in a DC motor is you actually create this magnetic field by replacing the permanent magnets with an electromagnet, and you can run it off of the same power source. So you take this battery and you actually run it over here, and you run it around a piece of iron, and you make this magnetic field. So you actually use the same power supply to make the magnetic field that you then use to provide the current through the armature, which then in turn makes the force. So with one voltage source you can actually get both of the components of electromagnetism that you need in order to make this DC motor. Okay, so let's look at another quick visualization here of how an electromagnet might work, and we'll see just really briefly how we're going to do this. And so this one is pretty... Okay, so here we are. So now in this situation, they're going to replace they're actually going to replace the permanent magnets on the sides with an electromagnet. And this is showing the iron rings right here. And you can see that they just wrap those things around there. They use a whole bunch of wires. They wrap it around. You run current through it. You don't have to alternate it. You're just trying to create that field, and then you're off and running. So that's how you do it. Okay, so that is the theory, or that's the engineering behind the DC motor. Okay, so one last time, just to kind of summarize that, is the science behind it is you noticed that you had, if you ran a charge, if charge was moving through in a magnetic field, it created a force. Engineers came along and said, let's build a motor out of that. So they made a loop of wires, and then they were able to use that loop to make it spin, and then they invented commutator rings in order to make it spin 100 or 360 degrees. So that's where they went, and then the electromagnet allowed you to remove the whole concept of permanent magnets. Okay, so that's kind of it. But now let's talk about just a few terms that you'll hear when you talk about motors on robots. One of the things that happens is that if you turn on a DC motor, you just hook a battery up to it, it spins really fast. I mean, that force really flips that armature around, and I mean, it can be hundreds of RPMs right away. And motors that spin that fast aren't necessarily super useful. Imagine wheels on a robot trying to spin thousands of RPM. I mean, it takes off too fast and you just can't control it. So one of the first things you want to do is you want to try to slow it down. And there's a variety of ways to slow it down. One way is to actually pulse the power to the motor. And so you think of it as, I'm going to turn it on and then turn it off, turn it on, turn it off, turn it on, turn it off. And so the motor will then never be able to get up to its fastest rotational speed. And so you can kind of regulate how fast it's going to go. So you do this by using this thing called pulse width modulation. And all it refers to is talking about driving the on signal at a certain percent and then the off signal at a certain percent, and they call it the duty cycle. So duty cycle means 20% of the time I'm on, 80% of the time I'm off. This duty cycle here is 60%, and 60% of the time I'm on, 40% of the time I'm off. And it's just a really simple way with a simple DC motor to kind of turn it on and off in order to regulate its speed. Now, I bring that up because you'll hear a lot of people talk about, well, the PWM signal is doing this, or I need a PWM signal. So this is just where it comes from. It's called pulse width modulation, and it's a common control signaling approach used in a lot of motor controller electronics. So it's good to just know what that acronym stands for. Another common acronym, or another common acronym, is BLDC, but this is a modification that was made to the DC motor. One of the problems with the DC motor is the brushes wear out and they get really hot and they can actually cause sparks. And you think about it, it's a brush that has the bristles on it are made of metal and it's rubbing against another piece of metal. So you know that's going to wear out over time, and it's also really noisy. So one of the advancements of DC motors was to figure out a way where you could try to make this thing rotate and get rid of those brushes. So they came up with this concept of a brushless DC motor. And the way that you do this, here's a very simple brushless DC motor. What you do is you go back to using permanent magnets. Okay, so you have these permanent magnets, and imagine that your rotor is going to now be on the outside of your device. So this is a wheel right here, and it's got north and south on here. And then what you do is you build electromagnets inside that are going to create magnetic poles when you turn them on. And what you're going to try to do is you're going to try to drag this north and south pole around here. So within here, you're going to have coils of wire around some ferromagnetic material such as iron, and if you turn it on, it creates a pole, and depending on the direction of your current, it could be a north pole or a south pole. So imagine that if you had a south pole right here, and you stuck this inside of your rotor, the part that's moving, you could actually pull that north pole over here, and then it spins over to the north pole. So you have a south pole here and the north pole spins over to here, and then what you could do is you could, as it goes past, you could switch the polarity of it, push it away, and then this one could turn on as a south pole and pull it. So what you do is the stator is now where the electromagnets are, and what you do is you pulse all of these what we call poles on and off accordingly in order to make this thing spin around. And what's really neat about this is that there's no contact. So this rotor spins around here and it doesn't make any contact. So this is really common in things like fans for computers that hardly make any noise, because you don't want them to be very loud, and you want them to last a long time. And so this becomes a very common approach. This is also what's used in drones. Now you do need a couple things in here. You need an electronic controller, and you also need a sensor. So they put sensors in here to figure out where the rotor is at any given time, and then that is fed back to the electronic controller, which then dictates which one of these poles you turn on and off in order to get the thing to spin. So that's the brushless DC motor. Okay. Another one of the most common motors that you see in robotics, especially robotics that are ground-based, is what's called a servo motor. So a servo motor is an assembly that consists of a couple different things. So the first thing that it consists of is a DC motor, and then it uses a gearing system to step down the rotational speed so that the final axle that you actually use is much, much slower than the DC motor. So you could have the DC motor spinning at, let's say, 500 RPM, and you can get this thing to spin a couple RPM. You can actually figure out how you want to do it. Now, in addition to that, one of the keys of a servo motor is that it has a sensor on it, so that the controller, the person that's sending the signal to this, the electronic controller, knows how many rotations that the DC motor has gone, so that it can actually regulate how fast or how much more it wants it to speed up. So it actually uses an electronic control signal. A lot of them uses pulse width modulation. But this is an example of what it looks like. I'm showing you that the LEGO Mindstorms motor motors are actually servos. Now you hear people talk about robots or robot motors, and they're like, well, my servos, are doing this. They're talking about a servo motor. The term servo, there's some debate about where this came from, but it was a French term, is where they think the first thing came from, and it was to serve the master, and the master being the electronic controller. So this whole concept of providing feedback of where the motor actually is back to the controller, it was serving the controller, and then that's one theory of where that name came from. So it's not like servo is a type of magnet or type of gear. It's just nobody really knows 100% where it came from. But all you need to know is that servo is a motor, DC motor, that is in an assembly that contains a gearing system and a sensor that then feeds back to the controller. Okay, now this is the inside of your LEGO Mindstorms motor. So you'll hear people when they talk about the Mindstorms, they'll say, well, are your servos, connected backwards, right? And with servos, they're talking about your motor. Okay, so that's it. So we just kind of give it just an overview of the science of what's happening in terms of the electromagnetism we can use electricity to cause motion. And that then became an engineering project which created the DC motor, and then there were some advancements to that. So at this point, we kind of understand some of the terminology, and we understand how you can make a robot move, especially ground-based ones. So we're going to say that Locomotion, we're going to give it another small check, because we want to do one more video where we start looking at, let's make our Mindstorm move. So now that we know the terms and know how it could move, I want to go in and let's start programming the Mindstorm to actually move forward and turn and try to start doing some very rudimentary tasks for us. Okay, and we'll do that in the next video.